Hey everybody, welcome to video 11. We're going to be looking at the applications now of the second derivative. Now this lesson will be just in one video instead of separate parts like the application of the first derivative, just to kind of keep things a little bit more streamlined. It will be a little bit longer of a lesson then, and so feel free to skip through some examples as you need to, because some examples do kind of repeat some of the processes just so you see it a couple times. But feel free to watch through all of it and go back and feel free to look at more of it. Now, the goals of this video is to introduce the ideas of concavity and points of inflection. And then the second goal here is to actually apply what's called the second derivative test. So we have a first derivative test and we have a second derivative test when we are testing critical numbers of a function to see whether that function has a relative maximum or a relative minimum at those critical numbers. And so we'll hit that last. We'll spend most of our time just in terms of the ideas of concavity and points of inflection and looking at some applications of them in a business sense and in one problem. Now, intervals and concavity. So starting here at this first problem, you may have talked about this in pre-cal. You don't talk about it very long, so it could be kind of faint in your memory, but hopefully the name of it sounds a little familiar. We're going to define this more mathematically here, and then using calculus, we can go through and find and determine the intervals of concavity for a function. So consider the graphs shown below, which give the estimated population of the world and of the United States through the year 2000. All right, so we're going 1950 to 2000. A here in the first graph will have the world population in billions versus the US population in millions in comparison here along the same time frame. And so what I want you to do is I want you to look at these two graphs and I want you to describe to me, or really yourself, since I'm just talking to you through a video, about how each part here, how would you describe the trend? Right, so if you looked at part A here, if you were to look at this graph here, what could you take away from this world population in billions? What could you take away from the US population in millions? Well, the first observation to notice here is that in both situations, A and B, so I'll just kind of say the world population, and then I'll say the US population. In both populations, we have increase, right? There is positive growth here in both populations. But how these populations are increasing are very different. For example, if you look at the world population and how it is changing, we start out kind of not necessarily flat, but as time goes on, the steepness of this graph continues to increase, meaning that in a shorter amount of time, the growth is very drastic from point to point. So the rate of change in and of itself is increasing as the function increases. Excuse me, versus if you look at the US population, it almost looks like the US population, although is still increasing in number, the overall rate of change is beginning to slow down and decrease as we trend along. And so I just want to kind of write that. So the world population, it's increasing, and the rate at which, I'll say the rate of change, is increasing. For the US population, the original function is increasing, but the rate of change, how that population is changing, is actually decreasing here because it's starting to flatten out. Now, in both of these situations, we know how to talk about increase and decrease in terms of calculus. So if both of these functions are represented as the letter f in both cases, because we're saying that f is increasing, then by definition, this is implying that f prime on this interval here is positive, right? That the first derivative is greater than 0. So that would be true for the US population as well. Because f is increasing, this means that my f prime is positive. But how would I mathematically describe these situations here in terms of the rate of change? Now, the rate of change for this function is notated as f prime. And when we say that f prime is increasing, this is saying that the slopes of the tangent lines are increasing, meaning that the tangent lines themselves are getting steeper as I travel along the curve. Therefore, for the US population, because the rate of change of that function is decreasing, we would say that f prime is decreasing. And how we would look at this geometrically again is this is saying that the slopes of the tangent lines, if you were to draw them for each point, would begin to flatten out. So their slopes are getting smaller in value, they are decreasing, and potentially could approach zero. And so this is kind of where we're at. Now, the second part here can be kind of weird, right? Because we're saying that f prime is positive, but f prime is decreasing. Versus for the world population, f prime is positive and f prime is increasing. That seems to correlate a little bit better because we tend to think positive and going up, negative and going down. And so this can seem kind of a conflicting issue. And so I want you to kind of think of a number line, for example, and I'm going to show this a little bit more in a minute. If you were to think about a number line, think about where you could have positive values and those values would be increasing. So you could essentially just say, well, Mr. Sanders, just 1, 2, 3, 4, 5, right? And we're reading this again from left to right. We have a very specific order. Well, each of these numbers are positive and each of these numbers are increasing. Versus in the US population, f prime is positive, but f prime is decreasing. Well, this just means I'm looking at numbers like 5, 4, 3, 3, 2, 1. Right? So again, all of these values are positive, but as I read the trend from left to right, these values are going down. So mathematically, what we're seeing then is when we're looking at the rate of change itself, that individual rate of change can either be going up or going down. And what that's looking at then is the curvature of the graph, which is what we call concavity. All right, now to help illustrate the tangent lines a little bit more, I have an example here, a graph taken from the book. That essentially has kind of like the world population here on the left-hand side versus the US, so it's a similar kind of growth. Notice that for the world population, all of the tangent lines sit underneath the curve. And so this is a kind of graphical thing that will always happen in this kind of scenario. But what I really want to kind of highlight here is if you look at each point that they chose on the curve, notice how the tangent lines themselves are getting steeper as we travel. So the slopes themselves have to be getting greater in value because we're getting greater rise over run as we travel from left to right. Versus in part B, where all the tangent lines sit above the curve, and notice that all of the tangent lines are beginning to flatten out as we travel from left to right, looking at these points that they've chosen. So that means I'm starting to get more run versus rise. My slopes are getting smaller and smaller in value, 1/4 versus 1/5 versus 1/6, etc. The fractions will get smaller and smaller as the denominator gets bigger and bigger. All right, and so when we're looking at this, essentially then what we need to do is look at, excuse me, look at this fact of, okay, well, if I want to look at curvature, which is defined as concavity, what we end up saying is that if my f prime is increasing, then we say that my graph is concave up. So A is an example of being concave, and the textbook uses upward, so I'll try to be fancy and say upward. When my f primes are decreasing, then we refer to this interval as concave downward, or just concave down. And so when we are trying to determine intervals of concavity, what we are trying to determine are these two pieces. What is happening with f prime? Is f prime in and of itself increasing, or is f prime decreasing? Now, this question here, although it may sound like it's a brand new question, is one that we've actually already solved in procedure. For example, really the only difference here is going through and saying f prime is increasing. Well, what if I just asked where is f increasing? Right? And if you've watched through the videos for the application of the first derivative, we know that when I want to find where is f increasing, then what we're looking for is the first derivative of f. Right? We have to derive it, and then we use the number line. Well, if I just add in the prime here, if I want to know where f prime is increasing, then what I'm looking for is what about the derivative of f prime? In other words, what if we were to derive it again? And then I'm looking for where that derivative is positive, because that would imply that f prime is increasing. And where is that next derivative negative, which would imply decreasing. So what we are actually looking for is the second derivative. And so if the second derivative again is positive, this is implying that f prime is increasing. It means that the slopes of f prime are going up. Versus if my second derivative is negative, then that is implying that f prime is decreasing. And that my slopes for my tangent lines are going down. They're starting to flatten out. And so we have this definition now as concavity. And so this definition is actually written out here. So the concavity of a function f. So let the function f be differentiable, meaning again that we are able to derive it on an interval from a to b. So if you were to pick two numbers, I can find the derivative for f and plug in any one of those numbers. Then we have one of two things. We can say that the graph of f is concave upward. So this is that concave up. If f prime is increasing on that interval, we can say that the graph of f is concave downward if f prime is decreasing on that interval. All right, and so here's our saying. There's a simple saying for concavity. So if we're talking about concave upward, generally what I will always tell my classes, and you hear this a lot in pretty much every kind of calc class, is when you are concave up, it means that your graph is shaped like a cup or a smile. When you are concave down, you are shaped like a frown. So you're shaped like this. And so the graph has to be one of these two curvatures, right? One of these two shapes. And when you look at these two shapes here, it can be a little weird in terms of this definition of saying, okay, in this situation here for concave upward, no matter where I am on this interval, I know that the derivative has to be increasing, right? So the tangent lines here would have to be getting greater in value. All right, and so I kind of want to pick a couple points like what we were looking at in the specific example earlier, and I'm just picking random points. And I just want to kind of sketch what that tangent line would look like. So this would be going down like that. This point it would be perfectly horizontal, and this point would be a slope like this. And if we were to pick values of what we thought this might be, we could say at this point for A, maybe A has a slope of -2, right? Because it's falling, so it's got to have a negative slope. Well, at B, this slope would be 0. And then maybe at C, we said this slope was something like 2, just to have some symmetry. Well, notice in terms of the numbers, -2, ... to 0, ... to 2, as I go from left to right, what's true about this list of numbers that we would get for these slopes? Well, these values are getting greater, right? So although these slopes are negative and then 0 and positive, remember we don't care that the tangent lines for this would be negative. We just care about what are the tangent lines doing in terms of their values, right? These values are getting greater. That means f prime is increasing in value, and therefore I'm concave upward. Versus when I'm concave down, if I was to pick 3 points again, just to help illustrate the point, and go through and draw their tangent lines like so, and say this is A and this is B and this is C, A could have a slope again, something positive, so maybe like 2 again. B could have a slope of maybe something like 0, and then C could have a slope of something like -2 because it's falling. Well, again, if you were to put this in terms of like a list, I would be going from 2 to 0 and then to -2, and these values from left to right would be decreasing in value. These were increasing. And so this would be an example, again, where all the tangent lines sit above the curve, and therefore I'm defined as being concave downward. Concave down, I'm shaped like a frown. And again, I think this is where some misconceptions can kind of come in, because although my slopes are negative and these numbers themselves would be getting larger in magnitude, right? This would be -2. The next one would have to be even steeper, so -4 and then -10. It can be really misleading because the numbers themselves are getting larger. The actual values, because they're being negative, or because they are negative, are actually getting lesser in value. And that's why we would go through and say that this is actually decreasing. We would look at it in terms of like a bank account, right? Going from -$2 to -4, you're not making money, you're losing it, right? Your value is still falling just into the negatives. And so that's something really important that I want to kind of make clear with this. All right, and so I've mentioned it before in terms of the definition, but we know now that if I'm looking for where is f prime increasing and where is f prime decreasing, then what we're looking for is the derivative of f prime. And if I want to take the derivative of f prime, that just means I want to get to the second derivative, or f double prime. That's my goal. And therefore, that's the title of this section, right? If I want to get to applications of the second derivative tells me about the curvature or the concavity of my original function f. And so I have that written out here in terms of theorem 2. And so it says that if f double prime is greater than 0, for every value in a specific interval, right? So from any two numbers that you chose, anything in there, if f double prime is positive, then that means that the graph is concave upward, because that means f prime is increasing, right? If f double prime is less than 0, so again, if the second derivative is negative on a specific interval, then we say that f is concave downward, because that is implying that f prime is decreasing in value. So like what we saw up above. And so if I need to go through and I want to find these intervals, we actually do this process very, very similar to how we did increasing and decreasing for f in terms of the previous two videos. All right, what we're going to do is we're going to go through and find the second derivative, and we're going to figure out where the second derivative is 0. Right? Because if I figure out where the second derivative is 0, then that means everywhere else, every other interval, the second derivative has to be either positive or negative. All right, then once we do that, we'll just use a number line and we'll plug test numbers back into the second derivative. That's really key here to determine if on that interval the second derivative is positive or negative. Then we can use theorem 2 to define that. And so I've got a couple examples that we'll go through and solve through. Again, looking for where a function is concave up and concave down. The answer again being an interval, right? We're looking over a series of values for x. All of these functions, again, will look familiar. Just kind of recycling through. So hopefully these derivatives, again, you've done this work already. We're just going one extra step now. And so in example 1, determine where the graph of the function is concave upward and where it is concave downward. So I know because I'm looking for concavity, that means that I need to go through and find the second derivative. Well, I can't find the second derivative without finding the first. So I'm going to go through and apply all the power rules to this. So derivative of x to the third is 3x squared. The derivative of minus 3x squared is minus 6x, and then minus 24. I want to go one more time, so I'm going to drive again. This was the importance of the higher order video. Derive it again, I just get 6x and then minus 6. And then I'm going to go through and set this equal to 0. So it's very similar to finding a critical number, but we are not finding a critical number here since we're looking at the second derivative. So that's something also I want to really clear out. But the process is very similar. All right, so I'm setting this equal to 0. So what I'm going to do here is just factor out the 6. And it's really just to kind of show you here that if this is equal to 0, then x has to be equal to 1 for this to be true. And so this is where the second derivative is neither positive nor negative. So it must be positive or negative everywhere else. And so to help find that, the tool that I'm going to use, and again continuously show you, is a number line. So I'm just going to draw a line. I'm going to mark 1 in the middle since it's the only value I have. And then I'm going to pick two sample values. Let's just say 0 and then positive 2 here. And I'm going to plug these back into the second derivative. And when I'm going to plug back in, I can either plug into the original or plug into the one that's factored. I'm just going to plug into this one here, just because it's x minus 1, so it'll be easier just to look and see what the numbers are. Because then I don't care about the actual value, I just care about the sign of that value. Is it positive or negative? So when I plug in 0 in for x to here, I'd get 0 minus 1, which is negative. So 6 times that just means this result is going to be negative. All right, if I was to plug in 2 minus 1 is 1. So then 6 times what that is just going to be a positive value. And so that means everything from 1 is going to be positive. And so now we can go through and determine my concavity, those intervals, based off of my number line. I know that I'm going to be concave upward on the interval from 1 to infinity, and then I will be concave downward on the intervals from negative infinity to 1. I said intervals, but just interval. It's just the one set. All right, so that's it. I mean, this is my answer right here. Perfect. All right, let's take a look at example 2. All right, so again, this one we saw before. So determine the intervals where the graph of the function f of x is x plus 1 over x is concave upward and where it is concave downward. All right, now for this one, just like we did for the applications of the first derivative, I'm going to rewrite it first to be x to the negative 1. This is just going to make the derivative a little bit easier to work with. So I'm going to take the first derivative. I'll get 1 and then minus x to the negative 2. We've seen this before. But again, I'm not going to stop here. I'm going to drive again because I care about the second derivative. So this will be positive 2 x to the negative 3 when I subtract again. And now it's the second derivative that I'm going to go through and set equal to 0. Because again, I'm only worried about concavity. And so then, because I have a negative power here, I'm going to rewrite it as 2 over x to the 3. And there's no way, there's no x value here that I could plug in to make this fraction here equal to 0 because there's only an x in the denominator. So there's no solution to this equation. But there is a value that x cannot be, which is 0. Right? And this is a point that I have to check, just like when we checked for critical numbers. This is still a value here because x can't be 0. It's going to break up my number line. And so it's something that I want to mark since the second derivative is neither going to be positive or negative there because I can't plug in 0 to begin with, right? And so for applications of the first derivative, I used a dotted line. I'm going to do the same thing here. In the original graph, this point right here would be marked by a vertical asymptote, so it has to break up concavity somehow. And so to figure out what that would be, again, we're going to pick test numbers, so something like -1 and +1. And I'm going to plug these test numbers back into the second derivative. Again, checking for signs. I'm going to plug back into here. If I was to plug in -1, -1 to the third is still negative. So that means this result overall will be negative. If I plug in a +1, it'll remain positive and overall positive. So this says that my original function here, this x plus 1 over x, if you were to graph it, what you would see is that this function would be concave upward on the interval from 0 to infinity, so everything to the right of the y-axis. And then I would be concave downward on the interval from negative infinity to 0, so everything to the left of the y-axis. And we've seen that this is proven and can analyze this just from doing the derivatives. So I don't even have to graph it to show it, but we could. Okay, so these two examples, again, just kind of illustrating the process, very similar to the first derivative. We go down to the second derivative, set it equal to 0, solve for x, or where x is undefined, or for the function is undefined, and then we draw my number line, and again, I'm plugging back into that derivative, that second derivative there, to determine, again, whether I'm negative or positive, because that's going to tell me about my concavity, right? Plus means concave up, negative means concave down, because that's describing how the first derivative is changing, whether that first derivative is increasing or decreasing. And so that's going to take us into the second topic here, which is called inflection points. So just like how the first derivative had critical numbers, the second derivative has what's called inflection points. So to help lead into this, here's kind of an application question. The graph below shows the total sales S of a manufacturer of automobile air conditioners versus the amount of money X that the company spends on advertising. And so what I want you to do is just kind of look at this graph here and just kind of analyze it and what we can kind of take away from it. And now they have this point here marked, so we know that it's going to be important. You can even see in the description here that the graph has a point of inflection. And so let's kind of look at what that means. If you were to describe kind of this scenario in terms of the business, how would you describe it? Specifically, as the business begins to spend money on marketing, how does that impact their total sales? So another way to kind of ask that question is, as I draw this curve here from left to right, how does this curve change? How is my sales impacted? Well, hopefully what you're seeing is that as this company increases the amount of money it puts into advertising, it doesn't see a lot of growth at first. You'll notice this curve down here is pretty flat, but as it continues to spend more and more and more, notice how steep the line gets until it gets to this point here at 50, 2700. After that, notice that it's essentially like the curvature changes, that it's going to stay along this path just for a little bit longer, but after I spend more than $50,000, the impact on sales starts to decrease, right? I don't make as many sales the more money I spend on advertising after this point. So notice below 50, as I spend more and more, I'm actually going to make more and more. But there's this kind of optimal point here, this changing point here, where I don't want to spend any more money because the return isn't as good. Well, this point and what we're looking at, if you're paying attention to kind of the words that I'm using, is this graph is concave up from 0 essentially to 50. Like notice even as you draw it, it's essentially the shape of a cup if you were to trace over it. Versus after 50, it would kind of start at a diagonal, but when I start drawing it, it would be concave down. I'd have to sketch it in terms of a frown. So there's a change in concavity at this point. There's a change in the rate that the sales, the amount of money we're going for, is changing, right? My sales are increasing, and the rate at how it's increasing is going up. But after this point, although I'm still selling more items, I'm not selling as many items as I was before. So its rate of change is decreasing as I continue to move to the right. So that's where this change in concavity, how I'm going from concave up to concave down. All right, and so this point of inflection is really, really important then, because what it's describing is it's describing a change in concavity. And so this would be one application where I would want to find that inflection point because it gives me kind of an optimal place to sell or optimal numbers here. And we'll go through and try to essentially find that in a minute. Another application, and there's a video called, I think it's 3 blue, 1 brown, or 3 brown, 1 blue, one of the two. And it's on YouTube, and it's a series that I've been working through sometimes with my pre-cal class and students. And so a shout out to him. He's a fantastic, not necessarily YouTuber, but he puts together videos and animations talking about math topics. And he put out one in terms of COVID-19 and this idea of flattening the curve. And so if you think about what it means and why we're trying to flatten the curve, what we're actually looking for is this point of inflection, right? If you think about infections and we think about viruses, we know that they're growing exponentially, but at some point that growth begins to stop increasing and that growth rate begins to decrease. And so it turns into what's known as a logistics curve. And so that point right there, it changes from being an exponential function to a logarithm. The curve will begin to flatten out. And so one thing that he was discussing, and I would encourage you to watch that video if you want to learn more about it, is he's saying that you should look at how many people are getting sick, but not the numbers, but how those numbers are changing from day to day. And it's at that point where you hit a maximum difference, and then those rate of changes begin to decrease. Do you know that you're actually getting to flattening the curve and starting to slow down the spread? And so that's a kind of another application here for the points of inflection and why this process mathematically can be so important in terms of its applications. For us, we're going to kind of keep things a little bit simple, a little bit more general, because that's just the idea for calculus. We'll come back and we'll see a couple business applications, though, towards the end, and you'll see some in terms of practice. And so if we're looking for points of inflection, and I'm looking for a change in concavity, again, like in this scenario or here, what's happening then at this point is a point where f double prime is not positive or negative. F double prime will be equal to 0, right? Or does not exist, right? We're looking for that scenario where that could occur. And so that would describe then a point of inflection if that point exists in the original function, right? And so we're looking for this part here, whether that second derivative is equal to 0. So the first derivative helps me describe critical numbers when I set it equal to 0. The second derivative helps to find points of inflection, right? It helps look for where the rate that something is traveling at, that rate of change, is going from increasing to decreasing or decreasing to increasing. I'm not sure if I said that one already, so increase, decrease, just in case I didn't say it. All right, and so I've got a definition here for it. So an inflection point, again, it's a point on the graph of a continuous function, so no breaks, where the tangent line exists and where the concavity changes is called a point of inflection or an inflection point. Both way is perfectly fine. You'll hear me use both. So observe that the graph of a function crosses its tangent line at a point of inflection, right? Because if you remember, when we talked about concave up, when you're concave up, your graph sits on your tangent lines, right? All the tangent lines are drawn below the curve. But when you're concave down, all of the tangent lines are drawn above it. So right, the graph sits below all of your tangent lines. So that means if you have a point of inflection, there's a change there where the graph essentially sits above and then below or vice versa. And so you see this here in the first example where you've got this tangent line right here. The graph ends up crossing over it where it's all the way to the left here. There's no piece of the curve that goes across the line until we get to this point. Same thing here, right? Everything is tangent line is below, now tangent line is above, right? Tangent line is to the right, now tangent line is to the left. It's this point where we can cross over it like that. So here's the following procedure. All right, this is very, very similar to what we've done before in finding critical numbers. Right, to find an inflection point, first step, find the second derivative. Next thing, like we've done before, determine the numbers in the domain of f, right? So we've got to be able to plug it back into the original function. It has to be a point where the second derivative is either 0 or the second derivative does not exist. Then we need to determine that there is a sign change, right? Concavity has to go from increasing to decreasing or vice versa, concave up to concave down or vice versa, for there to be a point of inflection. So we need to still do the number line and check for a change. Very similar to how we looked in the first derivative test to see if something was a max or a min, I needed there to be a change between increasing and decreasing. It's the same idea here. We're just going one level deeper and looking at the second derivative specifically. All right, so in example 3, find the point of inflection for the function f of x is equal to x to the third. So we're just going to start out really simple to just convey the main idea. All right, now I know I need to go down to the second derivative, so that's going to be my first step. First derivative will be 3x squared. If I go one level deeper to the second derivative, I would get 6x. And again, my task here is to set this equal to 0 and solve. Well, I know to just divide by 6, I get x is equal to 0. So this is a possible point of inflection. So just like critical numbers, I'm not sure if that guarantees it or not. So I need to go through and do a number line where I'm going to mark 0. And then I'm going to pick a value just to the left. So there's something like -1, just to the right, like +1. And I'm going to plug this back into the second derivative, and I want to check for sign changes. Right? So if I plug in -1 back into the second derivative, I would get -6. So that's negative. If I plug in 1, that would give me positive. So because there's a sign change, then there is a point of inflection at x is equal to 0. Now, because it's a point of inflection, saying x is equal to 0 is just telling me the x value where it could occur. It doesn't really tell me where the y value is. So if we were plotting this, which we will see in the video on Friday, is that if I want to get the actual point, then I need to take this x is equal to 0 and plug it back into the original function. So this would be 0 to the third or just 0. So this would be the y value. So therefore my point of inflection would be 0, 0. This would be my final answer because I'm looking again for a coordinate, looking for that point. All right, so let's look at a function that's a little bit harder. All right, so something that's a little bit different. So example 4, determine the intervals where the graph of the function f of x is equal to x minus 1 in parentheses, all raised to the 5 thirds, is concave upward and where it is concave downward. So very similar to the first part of the problems that we were looking at. And then find the inflection points. Because one thing that we could have done in example 3 is actually gone through and given the intervals for concavity, but notice it didn't ask that, so we didn't worry about it. Now we are going to go through and find all the different pieces of information. So I have my original function, so I'm just going to copy it down. So f of x minus 1 to the 5/3. All right, and then I know I need to go all the way to the second derivative, so I'm going to go through first derivative. This is going to be a chain rule, so 5/3, x minus 1, subtract 1 from the power, so give me 2/3. The derivative inside is just 1, so I'm not really going to go through and say times 1, because it's not going to do anything, so I just have this. I'm going to go through and go to the next derivative, so second derivative. Bring down the 2/3, this will give me 10/9, just multiplying numerator and denominators together. X minus 1 stays the same. Subtract 1 from the power, I get negative 1/3. All right, now my goal here is to set this equal to 0 and solve. So because I have a negative power here, I'm just going to rewrite it. So I have 10/9 x minus 1 to the 1/3. Right, this negative says it's going to go down and join any denominator I have. And like we've seen before, there's no x in the numerator, and there's nothing I can plug in down here that would give me 0 overall. So there's nothing I can plug in here to solve this problem. But one thing's for sure is I can't use 1. Because this got flipped to the denominator, I'm undefined at 1 in the second derivative. But I can still use that number in the original function, meaning it's not bad, and it means I can use it, right? I can go through the number line that we've done before, and it could still be a possible point of inflection, right? So I'm going to mark, so I know again for the second derivative, this would be 1. I can't use it, so I'm still going to use a dotted line for that. My sample point, I could do 0 or I could do 2. And then again, I'm plugging this all back into the second derivative, given that's where I am at. So I'm just going to kind of draw a line here to keep it separate. All right, so plugging 0 into here, this would give me negative 1 to the 1/3, which is still negative. So overall, this would be a negative result. If I plug in 2, that'd be 2 minus 1, so it's positive, and that'd give me a positive result overall. So notice that at 1 here, there is a change in my concavity. So that means that I do have a point of inflection at x is equal to 1 in the original function. I also know about my concavity, so let's go ahead and answer that. So I'm concave upward on the interval from 1 to infinity, and I'm concave downward on the interval from negative infinity to 1. Now, because again, I want a point of inflection, I'm going to take this x value, I'm going to plug it back into the original function. So again, this would be 1 minus 1 to the 5/3. This is going to give me 0 again. So then my actual point of inflection will be 1, 0. So together with my intervals for concavity, we have completed this problem. So let's take a look at example 5. This one's going to be a little bit longer because this derivative is a little bit more sophisticated, but I don't think it's terrible. And so we'll kind of walk through it together. I would encourage you to try this though before I work it out. So feel free to pause the video here and then try it on your own. The example states this: determine the intervals for the graph of the function 1 over x squared plus 1. Determine where this is concave up and where it is concave down, and then to find any inflection points for f. Right, so any points where this concavity could change. All right, so one of the first things I'm going to do here is just rewrite the problem as x squared plus 1 to the negative first power. Now the reason why I want to do this and not just immediately use the quotient rule is because this function has a constant up top. It means I can just flip this up and then I can just treat it like a chain rule instead of having to walk through the entire thing. Because if I was to do quotient rule, my f, which is this top piece here, its derivative is 0, so it's knocking out an entire section of the quotient rule. So it's just kind of trivial to go through and do that. And so I'm actually going to look at it like this. And so when I take this derivative, like we've seen before, this will be a chain rule. So negative 1 comes down. So I get negative 1 x squared plus 1. And then subtract 1 from the power gives me negative 2. So there's the derivative of the outside. And then I have to chain this by multiplying by the derivative of the inside, which there is a derivative now. So I need to go through and write that. Right? Derivative of x squared is 2x. The derivative plus 1 is 0. And so I do want to end up rewriting this, though, so that because this is a negative power, this creates a denominator. So I get negative 2x over x squared plus 1 squared. I almost forgot the plus 1. Now this again is just the first derivative. And so notice that at the beginning, again, I rewrote it so I could do just the chain rule. But because of that, and because the derivative is actually creating something on the outside, at this point it will be easier, because I want to derive it again, to go through and actually do the quotient rule now. All right, so I'm going to walk through the quotient rule. So in terms of the definition, this is my f, this is my g. And so quotient rule, remember, states do f prime, so the derivative of negative 2x is negative 2, and then multiply that by the bottom, x squared plus 1 squared. Then I'm going to subtract the derivative of g, so the derivative of x squared plus 1 squared. 2 comes down, take 1 away from the power, and then I need to multiply by the derivative of the inside. So all of this represents g prime for quotient rule. And then I need to multiply it by the top function, which is negative 2x. So here's my f. I just didn't want you to get confused by that extra 2x here. Remember, it came from doing the chain rule for this denominator. I have to multiply by the derivative of the inside. And that's where that 2x comes from again. All right, so I'm just going to kind of get that out of the way. Okay, so to finish the quotient rule, then I have the denominator squared. So x squared plus 1. When I square this is just going to double it and go to 4. So if we're looking at my numerator and denominator here, notice that I have in both of these terms, right, I have a highlight them. There's one term here, and then one term on the bottom, right? It's the subtraction that splits up the terms. Notice that each one of these things that I've highlighted, each have an x squared plus 1 in them. Like this first term has 2 of them. This only has 1 copy. The bottom has 4. So we can get rid of 1 copy from each set because that's the minimum that they have in common. And so I'm going to go ahead and cancel one of those out. So I'm going to do negative 2 x squared plus 1. There's only one of those now. Minus 2 times 2x times negative 2x. That one's completely wiped out. And then in the denominator, I would have 3 left over, so I'm going to write it. Now that simplification step you could do at the very end if you really wanted to, but I think it's easier to do it now. Again, the whole reason that I can do this now is because each term, each piece that I've got highlighted here, each has the same piece in common, specifically that parentheses of x squared plus 1. So I'm able to cancel 1 out because that's the bare minimum that each term has in common. All right, from here I can just go ahead and simplify. So distribute the negative 2. So give me negative 2x squared minus 2. Now here I'm going to get 2 times 2x times negative 2x. So that'd be negative 8x squared. With the minus makes it plus. This is all over x squared plus 1 to the third power. And this gives me the second derivative as 6x squared minus 2 all over x squared plus 1 to the third. Right? A really simple looking second derivative, but a lot of work to get here. All right, now remember that we're looking for concavity and we're looking for points of inflection. So once I get my second derivative, this is where my focus is really going to stay. And we're going through and setting the second derivative equal to 0. Now, I want to look for what will zero this out, aka really just where's the numerator equal to 0, right? This implies solving this part. If I'm looking for where this function is undefined, then I'm going through and setting the denominator equal to 0 and solving that. Now, the denominator will never be 0. And the reason why I know that is although this is being raised to the third power, the only way to get 0 is if the inside here is 0, right? It's the only way. Well, it's x squared plus 1, right? I need x squared to be a negative 1 for this to be equal to 0, and there's no way that can happen when using the real numbers. So there's no place here where the second derivative is undefined. So I don't have to worry about the denominator at all. So I'm just going to erase it completely. Instead, again, I'm just going to worry about the numerator. And again, the idea is that in a fraction, so in what we're looking at right here, the only way I can get 0 in a quotient is if I have 0 divided by something, right? The top has to be 0, and that's what we're doing here by following this arrow over to the right-hand side, right? And so solving this, I'm just going to move the 2 over, so I get 6x squared is equal to 2. Divide by 6, I get, this is 2 divided by 6, or 1/3, so I'm just going to go ahead and simplify it. Because now I'm going to have to take the square root, and this is where the numbers themselves can get kind of nasty. Now, when you write the square root, don't forget the plus and minus because we're introducing that in. There's always going to be 2 answers. And so I'm going to go through and kind of simplify our work a little bit. First thing I'm going to do is kind of bring this over here so I can have everything on the left-hand side and then do my number lines and stuff here. Now I want to work with this a little bit better because this just looks not good. Now a lot of this part is just algebra, right? Pretty much algebra 2. I want to split up the fraction into two separate square roots. Now I can do the square root of 1, it's just 1, and then I'm going to rationalize. So if you were looking in a textbook, the possible points of inflections would be at radical 3 over 3. Now these are also really, really important values because this is what I'm going to put on my number line. So you may look at it and be like, holy crap, that's terrible. It's not pretty, but these types of results tend to happen a lot in a calculus class. So just be aware of that and try to be as calm as you can when you see stuff like that. It's not that you're wrong. You're actually probably on the right track. All right, now in this number line, I want to go through and pick test values. Now here, to pick a test value, one thing I would encourage is just type this into your calculator. Right, this is just a number. See what that number is and pick a number less than that. One number that we could choose, if you just want to kind of guarantee it, is something we could do like -3. Here, we'll even do like -4 and plug that in. In the middle, we could plug in something like 0. And then on the right, we could plug in something like +4. All right, and then remember that I'm plugging this back into the second derivative. So I need to go through and plug these values back into here, which does not look like fun at all, just to be honest. All right, now we notice that the bottom is always going to be positive, so it's really just going to come down to what happens in the numerator. All right, if I was to plug in -4 into this derivative, right, into this piece right here, the top is going to come out to be positive, right? It'd be -4 squared and then multiplied by 6. Well, that's going to be a huge number. 6 times 16, so 72 minus 2 is 70, right? And this is all going to be divided by something positive. So that means that this entire thing will be positive here up until -√3 over 3. If I was to plug in 0, notice how the top would be 0 minus 2, so that's negative up top. On the bottom, you get 0 plus 1, so the result overall here is going to be negative. Then on the right-hand side, if we had to guess, if -4 was positive, so would +4. And you can check that again by using a calculator. And so this tells me now my intervals of concavity. I know that I'm concave upward on the intervals from -∞ to -√3 over 3, union √3 over 3, comma, infinity. Remember, the union means or. I'm concave up here, or I'm concave up here, right? It's between those two. Then I'm concave downward in between, so -√3 over 3 to positive √3 over 3. I'll get rid of that little dash, it's bothering me. There. So there are my intervals. This means because there is a change at these points, these x values here that we found are also points of inflection, right? That's where they occur. So now I need to find those points by plugging back into the original function, right? So again, I'm going to be taking numbers that aren't great and plugging them back into here or the original. Now, when you do that, the square roots will kind of get rid of itself since it's an x squared. So you can technically do this by hand and it's not terrible. You could also check your work by using a calculator. And so I would kind of encourage that. For negative √3 over 3, when you plug this in, I think you get 3/4. When you do positive √3 over 3, you should get the same thing. I'm just going to kind of look and make sure. So that would be 1/3 plus 1, which is 4/3, which should be 3/4. So that should be what you get in the calculator. So 0.75, if you're getting decimals, then you can convert that to a fraction. But that would be my points of inflection here. All right, here's a applied problem. So we're almost done. There's really only one example after this, I think. So applied example 6. So this is an effect on advertising on sales. So the total sales in thousands of dollars of Arctic Air Corporation, so something we saw a little bit earlier, who is a manufacturer of automobile air conditioners. That total sale is related to the amount of money that you spend on advertising, right? Getting your name out there. Now, the formula that they have come up with is given here by S of X. is equal to negative 0.01 x to the third plus 1.5 x squared plus 200. And this runs from 0 to 100. So $0 to spending $100,000 on marketing. And now what we want to do is we want to look for that point of inflection, right? Because we're looking for the optimal amount based on how that rate in and of itself, that change in sales, we want to know where it increases, and we want to stop right before it decreases to help make our decision. So I'm looking for that point of inflection, which means I want second derivative. So first derivative, I get negative 0.03x squared plus 3.0x. We saw this function actually before. I need to go one more time. So using power rule again, this would be negative 0.06x plus 3.0. And then because I'm finding a point of inflection, I care about the second derivative, and I care about setting it equal to 0. And so I'm going to solve this. Because my x here is negative, I'm just going to add it to the other side. So I get 3.0 is equal to 0.06x. Dividing by 0.06, I get 50. Now this again is just a possible point of inflection right now. We need to guarantee that it is by doing a number line. That's a terrible number line. I'm going to put 50 in the middle. I know because of my interval here, I could sit here and say 0 and 100. But again, we're going to pick test numbers that are fairly close to 50. Because I know it stops at 0, I could still use 1 though, so I'm definitely going to use 1. But on the other side, I'm probably just going to use something like 51. And then I would type this again into the calculator, especially because we're talking about x to the thirds and things like that, which can be kind of disgusting. Now, we're typing these in again into the second derivative. So I'm plugging this back into S double prime here, specifically this form. And I'm looking again for positive and negatives. So if you plug in 1, you'll find that S double prime will be a positive value. If you were to plug in 51, this will come out to be negative. So this is guaranteeing that at this point, I have a point of inflection, or at this x value. And so I need to find its y value. So again, to find its y value, we're going to plug back into the original function, and essentially we're just looking for what that total sales would be. And it's actually 2,700. This is the exact same graph that we saw at the beginning for inflection points. And so we actually have the inflection point of 50 and then 2,700 in terms of sales. Go back up, and I just want to make sure that number's right. I'm pretty sure it is. Concavity here. Point of inflection was 2,700. And that would be in terms of thousands of dollars. So 27, so I guess almost 2 million, right? 2.7 million when you fully look at it. All right, so this is actually the example that goes with that problem, which is pretty interesting. Okay, so what's the application of all this, right? So we've seen a use for points of inflection. We've seen how concavity can help talk about the rate of change for items. We've kind of highlighted a little bit in terms of how you could apply this to infectious diseases and things like that. In terms of maximum and minimums, though, we haven't really talked about that here, but there's actually a big test in a way that we can use our knowledge with the second derivative. And this is actually where the second derivative test comes in the second bullet point. Essentially, it says this, like if I know that I am concave up on an interval from A to B, right? So if I know that there is some graph here, and I know I'm concave up, so I have to be shaped like a cup in some way, shape, or form. Now, there's no guarantee that would be a full smile like this, right? We've seen before where to be concave up, I just need to make sure I'm still a smile. So something like this is concave up by technically. So what if I was to say then that there was an x value, so let's just say it's like a c, right? And it is in this interval from A to B, where I know that c is a critical number. In other words, that if I was to plug it into the derivative, the first derivative, I would get 0 or a DME, right? I know that it's a critical number. And if c is in that interval, then I know that the graph has to go down and then come back up, because this is the point at c. Because this right here is describing that the tangent line goes perfectly horizontal at this moment, right? There's a moment here where this has to occur. And so what this tells us then is if I know that my graph is concave up, and I know that this is here, then notice at this point, I would have a relative minimum. So how do I know I'm concave up though? right? Well, if I was to determine concave up, I would have to go through and find the second derivative, right? I'm going through and saying that the second derivative is positive on that interval. Well, if c is in that interval, then that means if I was to plug c into the second derivative, c has to be a positive value. And this put together is the first part of the second derivative test. What it says is that if f prime of c is equal to 0, right? If you find a critical number, and if you were to plug that into the second derivative and get a positive result, this means that the graph is concave down, concave up there, and c is that minimum. It's that lowest point. So then f, the original function, has a relative minimum at x is equal to c. Well, then this must be true then for the others. If I was to flip all this, right? Quite literally, if I was to talk about concave down on some kind of interval, and I knew there is a point c in that interval where the first derivative was equal to 0 there, meaning that I have a horizontal tangent line, because I'm concave down, I know the graph must be shaped like a frown. And if there's a point where I know the tangent line has to be horizontal, then the graph has to stall and flatten out at that point, meaning that at C, I'm guaranteed that this critical number is a maximum. Has to be. And so we could define that then in terms of if f double prime of C is less than 0, right? If I plug in that critical number into the second derivative and get a negative result, then that is implying I'm concave downward, and that means this critical number has to be a max. And so this put together is the second derivative test. So I have that actually listed out here in terms of what that test actually is. So we would compute the first derivative and the second derivative, which we've been doing already. I would actually need to find the critical numbers. So we would set the first derivative equal to 0 and solve. And then I would take those values of c and I would plug them into the second derivative. And what I'm looking for is just the sign, right? If I get a negative result, if I get something that's less than 0, that means I'm concave down, and therefore that has to be a maximum. If I get a positive result, I'm concave up, and that means a minimum. Now here's the interesting part. If I plug in c and I get 0, then there's nothing I know, right? The test just ends up failing, right? That it's inconclusive. I don't know if it's a max or min. It could be a point of inflection, right? If the second part is equal to 0, but it doesn't guarantee anything, right? In terms of just plugging in the number itself, we would have to look at the number line and look at the graph, and we have to do more. We might as well just go back to the first derivative test. And so let's take a look at an example of this, and then I'll end with a closure about why this test is important, why are there two tests, etc. All right, so let's take a look at this example. It's kind of the final example here. Determine the relative extrema of the function. So again, looking for maxes and mins for this function. We've seen it before, using the second derivative test specifically. So I'm not doing the first derivative test in a number line. Instead, what I'm going to do is find the first derivative. So I'm going to go through and find f prime of x. So that is 3x squared minus 6x minus 24. And then I'm going to go ahead and find the critical numbers. So I'm going to go ahead and set this equal to 0. And I'm going to go ahead and solve. Again, we've worked this problem in the previous videos. So you may already have this worked out. I'm just going to go through and just do the math fairly quickly. We factor, and I get x is equal to 4 and x is equal to negative 2. So these are the possible locations for maxes and mins of the original function. Now to determine what these are, the second derivative test tells me to take these critical numbers and plug them into the second derivative. So the second derivative would be 6x minus 6. And again, I want to plug these values into here, and the sign, whether it's positive or negative, will imply concavity, which tells me whether I have a max or a min, right? So f double prime of 4 would give me 6 times 4 minus 6. Well, this is 24 minus 6, or 18. That is greater than 0. So that is implying that my graph is concave up. Therefore, there is a relative minimum at x is equal to 4, because that 4 is right there. It's the bottom of that valley, right? If I go through and I plug in negative 2, This would be 6 times negative 2 minus 6. Well, this result would be negative 12 minus 6, which is negative 18, which is less than 0. So that implies that I'm concave down inside that interval, wherever C is, in this case, negative 2, meaning at negative 2, I have a relative maximum. So for the second derivative test, it's actually fairly simple to actually employ, right? All I'm doing is once I solve for the critical numbers, which isn't terrible and involves some factoring and things like that, I'm just now plugging into the second derivative and just seeing what kind of number I get out. And I don't really care about the 18. I care about whether it's positive or negative, right? Because that tells me exactly what I have. It can be a little confusing because in the second derivative, notice that if I'm concave up, I have a minimum. So the language, again, doesn't seem to correlate. But again, it will make sense if you think about the actual concavity. But again, this test is technically easier than the first derivative, right? It just kind of depends on how you feel about deriving. The issue when it comes to the second derivative test is that it can be inconclusive. So in other words, it doesn't work every single time, right? It's really helpful, again, if the second derivative is easy to find, because again, it's just plugging in numbers. So I can use a calculator for that and just plug and chug. But if I get 0 as a result from that, it means I can't use it, right? And that's kind of the issue, right? It's not usable for every single problem. The first derivative test can be used for every single problem, right? There are no shortcomings. The major complaint for it is that it just takes a long time because you have to do a number line, right? And that's the two different things, right? So you kind of have, again, the first derivative test, which is concerned with where a function is increasing or decreasing. So the steps were to find your critical numbers and then draw a number line, which can be tedious, right? For the second derivative test, you are finding your critical numbers, but then you're plugging them in to the second derivative, and you're checking for positive, negative, or 0, right? If you get a positive result, you have a minimum. If you get a negative result, you have a maximum. If you get 0, please try again, right? You'll play style, yogurt style, right? And so this is kind of the first two setups. And in terms of assessment styles, I will either give you a set of problems where I'll ask you to kind of walk through and do this, or I'll have you write up a couple functions and then I'll do some steps and see what you can do. But these are really, really important for curve sketching, which is what we'll get into in the video on Friday. And you've seen, again, some applications in use in business. Where I'll end, well, this video is already an hour, so I'll just go ahead and close out here. I won't go any longer. So let me know, take a look at the practice problems. Make sure to put a post in the discussion board about this, and then let me know if you have any questions, and I'll be happy to work through some stuff. Hope everything is well, and I look forward to seeing you all again.